So this will be the agenda for the day. First, we will start with the OPTEE and the OPTEE crypto layer overviews for those who are new to the OPTEE. And then we'll see how a key is generated and used in the OPTEE. We'll discuss the security view in the current implementation. Then we'll see some security vulnerabilities that are already found in the TE environment. And then how can we prevent the exploitation of those vulnerabilities using the hardware-backed runtime secure keys. And then in last, we will give you a proposal that how NXP is going to solve that problem. So this is the typical diagram of the OPTEE stack. It is divided into two parts, normal world and the secure world. In the normal world side, we are having the client application, TE supplicant, TE client APIs, and in the Linux OS, we are having the TE driver. And in the secure world side, we are having trusted applications, TA OPTEE OS, and secure monitor, which is basically responsible for switching the context from the normal world to the secure world. So there are multiple layers that come into picture whenever a crypto operation is called via TA. So let's say some crypto operation is called via TA. First of all, it will land into the libtomcypt, which is basically the implementation of the TE internal APIs. And then a supervisor call is made, which will switch the context from EL0 to EL1, and then our crypto layer comes into picture. So currently there are two crypto libraries present in the OPTEE, libtomcypt and mbedTLS, and at one time only one crypto implementation is active, and by default libtomcypt is used. And one more thing here, that if you want to offload some crypto operations to your hardware crypto engine, so you can also plug in your own crypto library here. OPTEE gives you this option also. So let's say a key generation operation is called via TA. First of all, it will land into the software crypto library by passing all the crypto layers that we just discussed, and the crypto library will generate the key and save it into the secure memory. Now, if you want to save this key for subsequent usage, OPTEE will encrypt this key using the file encryption key and save it into the persistent object in the root file system or RPMB, whatever the case may be. And the file encryption key, which is used for encrypting, is derived from our hardware unique key, which is specific to only one system. So if you get the access to this key, persistent object, and you want to decrypt it, this key on any other system, you will not be able to do that, because that is the key which is used for encrypting this key is specific to only one system. So we can say that this key is secured at rest. Now, if you want to use this key, first of all, this persistent object will be opened as part of the open call. That key will be loaded into your secure memory, and then this loaded key will be, along with the data, will be given to your crypto library, and what operation you want to do, that will be done, and you will get the result. So basically, this is the combined view of both the key generation and any operation which you are using, which you are doing with the key. So as we just discussed, that key, this key, which is in this file system, is secured at rest. But what about this key, which is in the secure memory? Are they really secure? I don't think so. No doubt they are in the secure memory and are protected from the access from the non-secure world. But what if any vulnerability come in TE implementation or TA implementation? Now let's see some of the vulnerabilities that are found in the TE. So this is a vulnerability I found it on OPTEE security advisory page. This is a pretty simple one. It was found in the syscall obj generate key system call. Actually, what it was doing that, what syscall obj generate key do, it takes the length of the key to be generated, type, and number of the attributes it should have, and then internally it allocates a buffer of size of the TE attributes into the param count, but without checking the integer overflow, if it is occurring or not. In case integer overflow occurs, it will result into the lesser heap buffer than the required. And then the user supplied params will be copied to that buffer, and maybe we result in the heap based buffer overflow with the attacker data written outside the buffer boundaries. So this vulnerability, if exploited, can result into the arbitrary code execution in context of secure EL1. One more vulnerability I found, it was found in the third-party applications on Qualcomm-based device. It was pretty complex one, so we'll not go into the detail of this. But it also allows the arbitrary code execution in the secure EL0 level. So basically, both of these vulnerabilities and other vulnerability can allow the arbitrary code execution. And if any attacker gets the access to the code execution in the secure world, it can leak our code, or it can leak our assets and the keys to the shared memory or something like that. So let's see if some hacker is able to exploit these vulnerabilities. So this is the view of our system. Let's say our memory is divided into three parts: non-secure memory, shared memory, and secure memory. And let's assume that this key, which we are using for the operation, is already loaded into the secure memory. And some hacker comes and he was able to exploit that vulnerabilities that we just discussed and lead to the execution of its own code. So which basically what does, it copies the key that is in the secure memory to your shared memory. Since shared memory is accessible to the normal world also, so a hacker can access that key and can so basically this hacker will be happy because it gets access to your data and something. So let's see how we can make this hacker unhappy. So we can prevent these kind of exploitation by using the hardware-backed runtime securities. What this term actually means, that all the crypto operations that we are doing are offloaded to our hardware security engine, whether it is key generation or any other operation, encryption, decryption, signing operation, all are offloaded to our hardware security engine. And hardware security engine gives and takes keys only in the encrypted form. It does not export the keys or your assets in the plain form to the secure memory. It always exports it in the encrypted form. And the encryption of these keys is done with some hardware key that will not leave your hardware anytime. So let's see what will be the flow if we implement this hardware security library with the which offload our cryptographic operation to the hardware security engine. Let's say a key generation operation is called via TA. Instead of going via the software crypto library, it will land into the hardware security library. Hardware security library will offload that operation to the hardware security engine, which will generate that key in the plain format. But the most important part is here is that whenever you want to export this key into the memory, it will not be encrypted as it is. It will be encrypted with some hardware key, and then only it will be exported to your secure memory. So rest operations will be same. If you want to use the save this key, that will be given to the OPTEE, and it will encrypt it using the FEK and all that. Now, if you want to use this key, first of all, you need to load this key. As part of loading operation, it will load the key into the, it will load the encrypted key now to the secure memory. And then this secure encrypted key along with the data will be given to hardware security library. Then hardware security library will give the data and along with the key to the hardware security engine. Now, what it does, first of all, hardware security engine will decrypt that encrypted key using the hardware key, and then it will use that key and the data to do the required operation. So we can say that our key does not come into secure memory in the plain format. So we can say that these keys are secured at use. That's why we derived the name runtime secure keys. Any questions?
So just a quick question, just to make it clear. Here, the key generation is completely offloaded into your hardware secure machine.
Yep.
Okay. So, and your hardware secure machine handles all the kind of keys that are currently supported by the OPTEE?
Pardon?
Like, well, it handles, I guess, key generation for AES key, but also ECCs and RSAs?
Yep. All types of keys can be generated in encrypted form.
So I have two questions.
Yep.
So first of all is that if you're able to derive all the keys on the fly, why export them at all? You can always rederive them as needed. And secondly, what about the RPMB HMAC key? Because that needs to be used actively by OPTEE.
Actually, we just thought of doing this user keys as of now. We will think about the RPMB HMAC keys afterwards. That is the future work we are planning.
And what are you using to encrypt those keys? What algorithm, what's the key strings, what's the key size? Because when you export those keys, you have to be able to encrypt them somehow. What are you doing to encrypt those keys?
You want to take that?
Are you talking about the keys which we are which are there in the hardware sec engine? Are you talking about the encryption over there?
I'm talking that when you export keys, you have to encrypt those before you export them out from your hardware secure engine. So
right. So
what's happening there? Currently
the hardware secure engine is using either AES CCB or AES ECB or CCM mechanism. AES symmetric encryption is being used by the hardware engine for encrypting those keys. And for exporting it out, we have something what is referred to as a blob format. So, because it will have to be stored persistently also for the persistent object. So for that, we have a hardware built-in mechanism called blob format. So, basically, you can equate this to an HSM also. Here, we are talking about encrypting and keeping the keys. It can also handles which are kind of given out of the HSM. So what we are saying is keys should not be exposed in plain format. The security engine which we are talking about over here has the capability where you can keep the keys in encrypted format, while you can also replace that with an HSM which kind of exposes the keys in the form of handles.
So let's see what happens when a hacker, what will be the state of the hacker when backed runtime secure keys come into picture. So we are the same system diagram is same. We are having the non-secure memory, shared memory, and secure memory, and we already assume that we are already loaded our encrypted key now in the case in the hardware backed runtime in the secure memory. Now same thing happens, but you will be able to copy that key and the hacker will be able to get access to this key, but that will not be of any use to him because that will be in the encrypted format. So what is NXP is proposing that the encrypted keys mechanism which we just discussed is NXP black key mechanism in the CAM block which we are using, which is our hardware security engine. So we can say that using the hardware security engines, we can protect the confidentiality and integrity of keys while we are using them. That is making them the runtime secure. And so we are proposing a generic framework in the OPTEE for seamless implementation of hardware-backed runtime security so that other vendors can also implement hardware-backed runtime security if their hardware is having that kind of support. We already did a POC for implementing these type of keys for RSA and ECDSA on top of the NXP CAM driver, which we are already in the progress of upstreaming to the OPTEE. For technical discussion, I have raised a issue on the OPTEE GitHub proposal. We can discuss the technical details there. So that's all from my side. Yep.
So regarding the OPTEE's use of the CAM hardware,
Yep.
When the OPTEE is using the CAM hardware, what are the implications with your rich operating system also wanting to use the CAM hardware?
Yeah, but there are multiple job rings which CAM exposes. So we can dedicate a job ring for the OPTEE OS also.
Does that result in a need to change the kernel driver for the CAM?
No.
Okay.
Basically, from U-boot itself, modify the device tree and not expose that particular job ring. You can modify the device tree and not expose that particular job ring to the kernel. So the kernel CAM driver would not find that job ring, and it would not be using that job ring. So that is how we currently do it.
At boot time, you need to make a decision that you will be using the OPTEE to talk to the CAM.
Right. So basically, you've done the resource division, and once you've done the resource division, when the device tree is being modified by the U-boot, so at that time, you kind of just take off that resource from U-boot.
Thank you.
So these job rings, they have some secure versus non-secure properties, right? So you can allocate certain job rings. I believe there must be some list of MMIO space or something in which you can, so they would be isolated using the secure versus non-secure bits or equivalent mechanism.
In the job ring itself, what we have is we have a bit which kind of indicates whether it belongs to the secure world or the non-secure world, and all the black keys and the black blobs stuff which we're talking about. Even if, because from the memory map, it's kind of, the non-secure world can also access the memory map of that job ring. Currently, that kind of protection is not there, but you will never be able to decrypt the blobs or the keys, because the secret source or the secret key, that is dependent on the trust zone property, the secure world property which is there. So that way, we're kind of protecting those keys.
Okay.
So first, thanks for sending the patches. This is a good thing. But I still think if I would have been the hacker here also, I can't get the key. But since I have the ability to actually run the code, I can load the keys and decrypt the data. So I can still get the data that we're trying to protect in this case. So this is definitely a step in the right direction, but I think there are more to it, some kind of access control or more, dividing it up in other pieces.
Yeah, that is a just start for this work. We will continue to evolve that.
One question, the access control would be kind of, we'll have to, whether it be this key or, plain key also, so the access control needs to be there. That is another problem which we kind of need to solve, right?
In the same vein, you mentioned handles, but if I'm an attacker, depending on how your engine works, I could just call the engine to decrypt the key and then before I copy it.
Yes.
So that part is the access control part, which we kind of still need to figure out how we work on that access control part. But here we're talking about when it's there in the plain part. So how do we do it? First step.
First step,
Yeah, and in addition to these comments, we should also think about revoking keys. So if you have an old key and it's wrapped in the blob format, and then along the way you want to revoke the key and renew it, you need a mechanism for that. The blob would not be relevant anymore in the future. It's also something to consider ongoing.
Okay. Any other question?
Just a clarification. So it's like, I'm wondering how this framework would be. I haven't seen the patches, but how this framework is going to go into OPTEE. It's like you have, say, some kind of a crypto library that's exposed to the user application, come into security L1, and then there's this framework that you access? So like
No. Actually, the slide which I just for the crypto API layers, that OPTEE gives you an option for plugging in your own crypto implementation. Overall, you will be calling the TE internal APIs, but underlying it will be our hardware crypto implementation or your software crypto implementation that you have to decide on the during the compiling as of now.
Okay, but it would be possible to, say, have hardware-backed implementations from other vendors.
Yep.
So the framework would be generic enough to
Yes,
kind of
that's
just have a
good.
plug-and-play kind of a
Yeah.
thing, right?
That is what we are trying to do. Yeah.
Okay.
Yes. Yeah.
I can repeat the question for the. This implies that it will have a hardware driver in OPTEE.
Yes.
For whatever hardware engine anyone wants to plug in.
Yes. Yes. Yeah.
Basically, we're kind of in parallel, libtomcypt is there, mbedTLS is there in parallel. So already discussions are ongoing on OPTEE list for that, for CAM and
Thanks for this. I should just say, in the longer term, I don't think it's going to affect this current work, and you know, it all sounds good, and you know, should proceed with these incremental improvements. But in the longer term, what ARM's trying to achieve is a standardized crypto API that should serve these kinds of needs that would be executing within a partition, actually, in secure L0 that all entities in the system could access. But that's a longer term plan.
Okay.
One question on that. With that standard crypto API, like I was also hearing with the PSA, that standard crypto API.
Yeah, that's what I mean, PSA crypto.
So, where in this OPTEE layer does it kind of fit? I mean, because currently, whatever trusted applications are developed, they use the GP API specification, and all the apps are developed based on that. So this crypto API would be exposed directly to the trusted apps, or where does this kind of fit in?
Yes, it would sit within it. It would be a trusted app itself or a secure partition.
So we're saying that instead of
available to the other secure apps or OPTEE or the normal world as well. This would be alongside. We're not trying to replace GP. You know, GP is still applicable to many segments. The idea is this would be more kind of segment-wide and applicable to all segments. So, in addition to that, there would be, you know, we're looking at kind of shim layers that talk between the two for applications that want to talk one API over the other.
Okay.
So to relate to what Dan has just explained, I think it's really important to consider support for key handles. This is part of the story. Maybe it's a different discussion, but it's part of this proposal, I believe. It can enable a lot of other future features, such as access control. So, and I think it's inevitably a part of the crypto API, anyhow. So it's an enabler for a wide range of use cases.
Okay.
Not sure it filtrates to this discussion, but we should probably see how the key handle issue goes on in the roadmap to part of the crypto API.
Okay. So, thanks all.